Hello all. In this second lecture of linear vector spaces, we will be discussing linear dependence, basis and dimensionality of linear vector spaces. If you consider a set of vectors 1, 2, etc. up to n in a linear vector space V, and if it is possible to express all the vectors in the vector space V in terms of these set of vectors, then we can say that this set of vectors span the vector space and they are called base vectors or basis of the vector space V. Suppose you consider the three-dimensional Euclidean space. We have unit vectors I, j and k, isn't it? That's what we have represented here generally. E1 is given by 1 0 0, E2 is 0 1 0, E3 is 0 0 1. You express every vector in three-dimensional space in terms of these unit vectors, isn't it? So you can say that these three vectors span the three-dimensional Euclidean space. But if you consider another set of vectors in three-dimensional space, is it possible to express all vectors in terms of these as a linear combination of these three vectors? No, it's not possible. This is a basis, but this is not. So you can say that these set of vectors E1, E2, E3 span the three-dimensional Euclidean space. Similarly, for any vector space, you can find out a set of basis vectors in terms of which all vectors in the vector space can be expressed. Such set of vectors are said to span the entire vector space and they are called base vectors or basis vectors. Now, if you consider a finite set of vectors, say 1, 2, 3, etc., up to n, and you are writing a linear combination of these vectors with coefficients ak for corresponding vectors k, where k go from 1 to n. If you are not able to find out any non-zero value for these coefficients such that this equation holds, then the set of vectors are called linearly independent. That is, for this equation to be satisfied, you can find out different values of ak, isn't it? If you are not able to find out any non-zero value of ak which satisfies this equation, or in other words, only when ak's are 0, this equation is satisfied. If such is the case, then the set of vectors 1, 2, 3, etc. up to n, they are called linearly independent. Or you can say that one vector cannot be expressed in terms of the others. Then such set of vectors are called linearly independent. Our unit vectors are an example for linearly independent set of vectors. You can't express this unit vector in terms of the other. So such set of vectors are called linearly independent if you can't express any one of them in terms of the rest n minus 1 vectors, you say that they are linearly independent. On the other hand, linearly dependent would be any one of these vectors can be expressed in terms of the rest n minus 1 vectors. Then you say that the n vectors in the set are linearly dependent. Okay, now let's see a few examples. Just as we said before, are unit vectors which span the three-dimensional Euclidean space. They are linearly independent. So how do we just check whether they are linearly independent or not? You write a linear combination of these three vectors and try to obtain null vector from this set. So how do you write it? A1 times the first vector, A2 times the second vector, A3 times the third vector equal to 0. Can you find, okay, what equations do you get? A1 times 1 equal to 0, isn't it? A2 times 1 equal to 0 and A3 times 1 equal to 0, isn't it? So anyway 1 is not going to be equal to 0. So the only option is A1, A2, A3 have to be 0. So other than 0, no other values of A1, A2 and A3 satisfy the equation. Is it clear? So these set of vectors E1, E2, E3, they are called linearly independent. Now you consider another example. If you are given three vectors 1, 2 and 3, you can try out like this: a1 times the first vector, a2 times the second vector, plus a3 times the third vector, and you try to construct a null vector out of this. You can see that these set of vectors are linearly dependent because you get that 3 times the first vector plus the second vector minus the third vector, it's possible to obtain null vector. Or 1 can be expressed in terms of 2 and 3, 2 can be expressed in terms of 1 and 3 in terms of the other two. So such set of vectors, they are called linearly dependent. I would encourage you all to just try out and find this relation. Just check whether it is so. Now let's go for another example. You are given set of 4 matrices like this, where each one each matrix is like one is changing positions. In the first vector, one is here in the principal diagonal in the top left. In the second vector, one is here in the off diagonal at the top. A third vector is like this, and fourth vector is like this. And these are the basis vectors for the vector space M22, which comprises of all 2 by 2 matrices. Okay, in terms of these matrices, you can express all the 2 by 2 matrices in the vector space M22. Now you can just see whether they are linearly independent or dependent. You can see that A times this one plus B times this one plus C times this one plus D times this one. There is no A, B, C and D other than 0 which satisfies this equation. Okay. So these are 4 linearly independent vectors in terms of which you can write any square matrix, any 2 by 2 matrix in this vector space. So these are the base vectors in the M22 vector space. Okay, now let's see what is the dimensionality of a vector space. The space which we are living in, we perceive it as three-dimensional, isn't it? Now, how do we get the notion of dimension of a vector space, of a linear vector space? If you consider the three-dimensional Euclidean space, there are 3 base vectors which are linearly independent, and you can express all vectors available in space in terms of these three linearly independent vectors. Similarly, if you are considering a vector space of dimension n, then that dimension is actually the number of linearly independent base vectors that span the vector space V. Just before we saw four matrices like given like this, vectors 1, 2, 3 and 4, and we saw that these four are linearly independent, and any square matrix in the vector space M22 comprising of all 2 by 2 matrices, they form a four-dimensional space. Why? Because there are four linearly independent vectors in terms of which all matrices in the space can be expressed. Okay, so the dimensionality of a vector space is actually defined by the number of possible linearly independent base vectors in terms of which you can express every other vector in the vector space. I hope it's clear. So, any square matrix in this M22 space can be expressed as a linear combination of 1, 2, 3 and 4 vectors. Now, if A, B, C and D scalars are real, we have a real four-dimensional space, whereas if they are complex entities, you have complex four-dimensional space. So I hope the concept of linear dependence, linear independence and base vectors as well as dimensionality of vector space is quite clear. You may refer to the textbook authored by Tai L. Chow on mathematical physics, mathematical methods for physicists. You can refer to the textbook for further details. Thank you.